my first talk after more than 2 years, so very glad. And the research I would like to tell you today is a research that I made in collaboration with Rafael Ortega, professor at the University of Granada, and a very close friend of mine, that is Gian Maria Gazzini from the Polytechnic of Milano. And now, okay, here is an overview of my talk. I will, first of all, so this will be a very theoretical talk, and so I will try, first of all, to introduce the methods that we are going to use. Then I will state the main result, and then I will give an heuristic derivation of these results. And then I will try to, if I have time, but I think so, to give the outline of the proof, both in 2 and 3 dimensions. So let us start with regularization techniques. So it's a matter of fact that in celestial mechanics, as far as in atomic theory too, collisions are important. And also interesting. From a practical point of view, of course, but also from a theoretical one. A collision is what you can imagine, is when two bodies has a mutual distance that tends to 0. Okay. So I will talk about singular set of the dynamical system. For me, a singular set are the point of the space where the collision takes place. So, for instance, if you consider just the Kepler problem, very easily, the collision just takes place at the origin. Also, this is the anisotropic Kepler problem. While when you deal with many bodies system, the collision set is a conic set. Okay, is the union of hyperplanes. Now, more than 1 century ago, some mathematicians, starting with Levi-Civita, Birkhoff, and many others that I listed there, and I just listed the main names, try to propose some techniques to regularize the singularity. What does it mean to regularize a collision singularity? This is a sentence that I took from a paper from Alessandra Celletti. It's a survey paper on regularization that I love. And she explains that the aim of regularization theory is to transform a singular dynamical system, typically a Newtonian dynamical system, but anyway singular, into a regular one. And to provide, and this theory generally provides a mathematical tool to analyze motions leading to a collision or near the collisions, and maybe also to extend this motion after the singularity. This is I think that this is a summing up of what is a regularization technique. Then the second ingredient of what we have done are variational techniques. So what does it mean to try to use a variational technique? A variational technique is a branch of analysis where you try to find solutions of system, of an ODE or PDE or whatever, as critical points of a suitable action function. Action functional, Montpellier functional, Jacobi length, depends on what you fix in your problem. You can fix the period time, you can fix the energy, or so on. In the 90s of the last century, so more or less 30 years ago, starting from a big work by Vivina Barutello, this kind of methods have been applied to singular problems. So problems linked to potentials of this kind, not only of this kind, but of these kinds. Okay. And quite immediately was clear that these techniques as a problem in their application to this kind of dynamical system, because there was a lack of compactness. compactness is a property in a functional space that ensures you that if you take a sequence, this sequence okay, this special sequence admit a convergent subsequence. Okay, this is the spirit of variational methods, to approximate critical points with sequences, but to converge the critical points, you need a sort of compactness. Okay, and you don't have it in this singular problem. To obtain compactness, typically symmetries or topological constraints are involved. Okay, so symmetries are really okay. There are many symmetries that you can think, but also very simple symmetry. For instance, anti-symmetric orbits, or also very simple stuff. You have a very simple example, a very complicated one, but anyway, symmetries. And this kind of constraints, so symmetric constraint or topological constraint braids or other stuff, are put to try to obtain this convergence of sequences to critical points. Okay? So once that the theoretical building is built, and so the solution of the problem is produced, it turns out a fact. It turns out that the critical point that you have found can interact with the collision set. Indeed, what happens is that the functional, for example, the Lagrangian action functional, but also the others associated to this singular problem, here, for instance, also the Kepler problem, are finite even though the solution has collisions. And so it is absolutely natural to find a collision solution when you apply variational techniques. Okay? So this is the fact. So in some sense, variational techniques are also, if you want to see it from a positive point of view, are a good tool to investigate collisions. Okay? And so now you have your candidate to be a solution. What do? Near collisions. You make an asymptotic analysis. You make a blow up. To make a blow up, what does it mean? It means that you look near the collisions and you make the picture bigger and bigger. This is to make a blow up analysis. And then you make an analysis trying to extend the flow at the singularity. Okay. Once you have done this, more or less this step, you can try, and it has been done in many situations, you can try to prove that these solutions, this motion that you have found, indeed don't have any collision. Okay. And you can prove this absence of collisions, and so you can prove that your solution found by variational methods is a real solution of the dynamical system. You can try to perform this to do this proof by level estimates or by other interesting stuff. So, for instance, Marshall lemma. There are many interesting ways to do this. Another thing that you can do, and this would be more or less the content of the next seminar, you can also try to determine the contribution of collision to the index. Here, to the Morse index, maybe there are also other indices that are suitable, to the Morse index of a solution, in order to try to give some classification of the colliding solution with respect to indices and so on. This is I think this is a really challenging research. Okay, so these are the two main ingredients of what we are going to do. But I just repeat one thing, that typically in a variational method, you take your functional, that is an action function about a tree or something. You look for critical points, gaining compactness, maybe putting some symmetry. You find a critical point, and then you try to understand if these critical points has collisions. This is the natural steps. What we are going to, what we have done, what I'm going to try to explain now, is something that goes in another, a little bit in the opposite direction, if you want, because first we try to regularize the functional. Until we first we regularize the functional, then we prove that the critical points of the new functional are suitable. I wrote suitable here, solutions of the starting problem. Now I write the problem. In the next slide there is my problem. Okay, suitable solutions of the start of the problem, and then we prove the existence of critical points of the new functional. These are the steps. So in some sense, what is new is that we first try to regularize. Okay, this is the basic idea. So let's go to the problem. So the problem that we consider is the perturbed Kepler problem. And the results that I would like to present are linked to the presence of periodic solutions. There are also other results linked to the Dirichlet problem, but I think that are less interesting. So I just focus on the periodic situation. So this term here, the first term is periodic. It's periodic and regular. It's C1. Okay. The dimension. Okay. A priori, you can take any dimension you want, but the truth is that the more interesting results we find are in dimension 2 and 3. Okay? In dimension 1, everything is already well known, I will tell you, but so you can think dimension in the plane or in the space. This forcing term here can also be replaced by a term of this kind with a bound on the growth of the potential on X. I just put P because the computation, also in the paper, just P, because the computation are a little bit shorter, okay? And so it is well known the classical solutions, of course, of this dynamical system here are solutions that do not touch the origin, because in the origin the dynamical system is not defined simply. But let us try to understand what is the meaning of the word that I put here, suitable solutions. For us, suitable solution is what we call generalized solutions. Okay. Let us try to understand what is a generalized solution. It is something very natural because it's a concept that comes from the regularization. So just think to the Kepler problem with a fixed energy and so semi-axis. Okay, I also fix the direction of the semi-axis. The energy is negative, ellipses. This family of ellipses, as the eccentricity approaches 1, converges to the ejection collision solution. And I would like to observe that this more or less green solution has this particularity that you can imagine to extend it to a periodic solution, okay, with constant energy. So this solution goes into the origin and then goes back with the same energy and with the same direction. Okay, this is maybe an idea that also motivated the study of Levicivita in what I say, I will tell about. I think it is contained in the first paper, but these are the two main papers on this subject. So, Levi-Civita, the idea of Levi-Civita is to propose a regularization of the motion. That is this one. There is a spatial regularization here in space, and this one in time, so that here is just the Kepler problem, so that the dynamical system and the energy becomes these two quantities, a very simple computation. And if you replace this quantity here into the energy, you find the harmonic oscillator. Okay? That is no more singular. So you solve the harmonic oscillator, and then you try to go back to the variable x. And what happens? If you go back, what you find is that you can go back, first of all. You can go back. So you assume that you have a z that satisfies these two equations here with h negative. You invert the time relation, the x is the square of z, and you really find the solution for the Kepler problem. Okay, here it's a little bit simplified, but the idea is this is the idea. And this solution that you find now has also a meaning when an isolated collision occurs. In particular, if Z is smooth, then X preserves both the energies and the direction of collisions. It is exactly actually the picture that I show you, but this is also behind this regularization. And so the definition of generalized solution now is natural. A generalized solution is a solution of the perturbed Kepler problem that of some interval is continuous. It admits at most a discrete set where it vanishes, this set Z here, and for any open interval that does not intersect the collision set, so it's contained in J minus Z, the solution, this function is a solution of the classical problem. Furthermore, this is the assumption. Assumption number 3 is the one that I try to motivate. Furthermore, if you consider a point in the collision, an instant in the collision set instance, then both limits of positions and energy exist. Okay, so let's say through collisions, the generalized solution keeps the energy and the direction. This is the idea. Okay, it's just a remark. Okay, in literature, the notion of generalized solution was already present, but in the works of Vivina Barutello and also in many others, here I just mentioned this one, but they're not the only works. Generalized solutions are solution of autonomous singular Hamiltonian system that preserve just the energy. Okay, the position is not preserved. So this is the difference with respect to this group of works. It's a big group of works. These are just the main ones. And okay, the direction, there was just a paper, as far as I know, a paper from Tanaka, where also the direction was conserved, and it is the case of collision break orbits. There are orbits that touch the origin and then goes to touch the boundary of the distribution. Okay, Tanaka called them collision break orbits. So the notion of a generalized solution that I use, it is not only natural for the regularization theory, but it's a notion that has already been used. First of all, it has been introduced by Rafael Ortega in a paper when he proved the existence of infinitely many periodic solutions in one dimension. And then it has also been used by Alberto Boscagin, Ortega, D'Ambrosio, Patini, Reizao, a group of persons that work on also computing work on this subject. But their results are valid here just for small p, not for every p. So they just use just is not the right term, but they use some perturbative techniques to obtain this result. So this result holds for small p, while here in two dimension, Alberto Barutello, these three authors, found this a very nice result that indeed they obtained while we were writing our result, so we were very worried about it. But finally they found a result via variational techniques of just one solution for every p in two dimensions. Okay, now I will state our theorem. Then there are also other contributions by Leizao, by Carvalho and her student, and I don't see many others results about this plot. Okay. This is our theorem. Our theorem is, our main result is the following. In dimension 2 and 3, you can take the force that you want, so just a periodic force, but without any other assumption, just regular, case 1. Then the perturbed Kepler problem has infinitely many periodic generalized solutions. Okay, so we have an existence result and a multiplicity result for any forcing term P. We prove the existence, so the strategy of the proof is that we prove the existence of infinity many critical points of a new function that now I will find. Okay, and such critical points actually turn out to be generalized solutions. Okay. So when we started this research, our aim was to obtain a result of this kind. I mean, our aim was to find a multiplicity result for the perturbed Kepler problem, and this is what we have done. But after that we proved the result, we remarked that the strategy that we adopted, that is to write this new regularized function, can be a strategy that could be applied also in other situations. Okay, so the idea was born really to study this problem, I must admit, but finally, now in this period, there are the group from Augsburg of Urs Frauenfelder, Reizao, and other collaborators applied this technique. They contact us to know that they are working on this. They applied this technique to many situations, many interesting situations of, let's say, in general, Hamiltonian equation with a delay. Okay. For instance, the first paper that they wrote on this subject is this one. There are up to yesterday, there are, I think, 6 or 7 papers on active in the last year where they apply this technique to many different situations, and we are very proud of this, I must admit. And for instance, here the frozen planet orbiting the helium atom is a model, an atomic model, where there is an atom of helium that has a nucleus with 2 electrons on a straight line, and they study the periodic solutions of the middle electron using a mean, an interaction in mean. Okay, and they use this technique. Really recently, I think it's something in the last weeks, they also try to generalize, to apply this method of regularization that I will explain, it's a non-local regularization, to obtain the computation of topological indices, as we call Alexander index, to the to some classes of derivations. Okay, this is I haven't read completely this paper, but I'm happy that somebody does this stuff. Now I will try to give you an idea on how to find out this regularized functional. So we started from the classical action functional associated to the problem. It is well known that this action functional is of class C1 on, okay, now here I'm working with periodic solutions, okay, so I focus on periodic, but it is well known that the action functional is of class C1 on periodic loops without collisions that do not interact with the singular set, and the critical points of this action functional are classical solutions, okay, in this set, of course. As I have already mentioned at the beginning, to overcome the possible occurrence of collision in finite action loops, because it can happen that collision occurs with a finite action, then you can put some symmetries on the loop space here. But to put some symmetries on the loop space means to require symmetry on P, on the forcing term P, and this is exactly what we don't want to do, because we were looking for a result for any P. So we tried to pass to a regularized functional. And so we made a variable change that is in the 2 dimensions, the variable change proposed by Vivina. So we made a variable change in this functional here to obtain a new one. This situation is not, I mean, you can think that, okay, you have a functional, you already know that the critical point of this functional are solutions, then you can also think that you change the variables, you find a new functional, and the critical points of the new functional are these solutions. This is not, I think it's not what you see, but this is not the truth. And so the link between the functional A, the functional B, and the original problem is quite tricky. Okay. So the variable change that we use, the same variable change that Vivina used. In particular, there is a time scale that is the classical proposed by Surman too, and a spatial transformation. The time scale is done for every, it depends on the loop, okay, this is the fact. So the time scale, which depends on the loop, is done on every loop with finite action. Indeed, this integral here is finite. While the spatial transformation is a transformation that fixes the sphere, okay, and is homogeneous of degree 2. So, for instance, the square. So, now assume that there exists a motion, a loop, a small x in capital X, that is the image with respect to phi of a loop Z. Assume this. And let us write this functional in terms of phi. Okay. This computation is long, but finally you find a functional of this form where the quadratic part here, the kinetic part corresponds to this term here, while the potential part here, 1 over x, corresponds to this 1, okay, one is in front, the inverse of the L2 norm, the square of the L2 norm of Z, while this term here transforms into a term here. So, if you at this function here, you remark that if these two terms are quite well done, and they are, then the singular, there is just one singular point for this function, that is the loop that is constantly equal to 0. Okay, so you don't see anymore this denominator here. Okay, and this denominator here became just an L2 norm. Okay. Here just something more on this function. Of course, Q and R depends on the choice of phi. R is always C1, does not depend on the choice of phi, while the regularity of Q depends on the choice of phi. The new function contains these non-local terms. Okay, these two non-local terms. That is the reason why it can be used for delay equations. And here I wrote the three main situations that we analyzed. Not the three main, the only three situations that we analyzed. Oh, sorry. The first one of the most general one, for any dimension, we take this function phi, and the term Q becomes this term here. While if you work in 2 or 3 dimensions and you consider the Levy-Civita regularization, or this is a little bit different, but the Custanemo-Stifler regularization that now I will explain a little bit. The term Q just reduces to the L2 norms of the Z prime, and Z was in H1, so this is a finite quantity which was defined. Okay. The Custanemo-Stifler regularization is a sort of extension of the Levy-Civita regularization. There will be a talk in the afternoon by on this subject. And the way that we use this regularization is by means of the quaternionic structure. It's quite normal to do that. And the function, the homogeneous function phi that we consider is this one. Also, the role of this function is important in this transformation in each one that we consider. So, our goal was to, as I wrote before, was to develop this method in 3 steps, and now we have done the first one. Okay, because we have regularized the action function into a new functional B, at least, okay, at least for 2 and 3. Also in this case, it's regular, okay? Regular here, you don't see any similarity. But the situation is a little bit more tricky, but we will see this in the previous slide. Sorry, it's the period of the solution, of P. It's the period at the beginning of everything. It's a number. Anyway. So the second step is to find the link between critical points of the regularized functional and the generalized solutions. Okay. Also, this link is not so straightforward because you can construct a counterexample, also very easy, simple counterexample, as the one that I brought here, for which you have critical points of the new function, but this critical point does not preserve the direction. Okay, these are a stupid counterexample, but it's thoughts. And you can also construct many strange things. So for which, in this case here, this functional here you can say that if you have a critical point of P, then you go back to generalized solution. This is not good. You need a further assumption, but I will not talk about that. I will talk about the bidimensional case, because this is the case where everything works. Okay. So in this case, you take the Levi-Civita transformation, the spatial Levi-Civita transformation, okay. And your functional with your new functional reads like this. It is a very nice function because these are the L2 norms. You have an L2 norms at the denominator, so that B is not defined at on the zero loop. And then you have another part here that is not so bad. Okay, it's not so bad. And what we can finally prove is that any critical point of this functional, where is defined, I think so, not zero. Okay, any critical point of this functional is a generalized solution for the Kepler problem. So now, if you can apply variational methods to this functional, you will find good solutions, let's say natural solutions. Okay. The proof of this fact is not trivial. It's done in many steps. Here is the precise statement, but it's not important. The proof is done in some steps. The first step is to find out the Euler-Lagrange equation associated with the functional. It's quite a tricky functional. So find out the Euler-Lagrange equation took some moments, but then you find this equation that are integral differential equation. Then, starting from these equations, you can prove that critical points are regular, that has only isolated zeros, that the map is invertible, that it is smooth. Then this is funny because you prove in two steps this fact. First, at least we proved in two steps, maybe you can find something different. But first, we prove that on every interval without collisions, not exactly the perturbed Kepler problem holds, because in our problem here mu was equal to 1. Okay, but another problem holds with some positive mu. But finally, you can show that these mu are or equal. This is something that holds in 2 dimensions, but not always in 3. Okay. And so finally you prove that X is a good solution. Okay, so this is the outline of this very short outline of this book. So now we've done step 2 done. So now we have a good candidate to produce solutions. We would like to find solutions. So now we want to find, of course, the periodic generalized solution for the initial problem. We should be tempted to look for critical points of this functional on periodic. Well, this is natural. Okay. But unfortunately, if you look just for periodic solution, also this new functional does not satisfy what is called the Pallet-May condition. The Pallet-May condition is a compactness condition. Okay, and so the tricky stuff is the following: is that since the relation that you have between x and z is this relation here, x equals z squared, is not necessarily z has to be periodic, but can also be anti-periodic, because when you make this square, this minus here becomes a plus. And this helps you a lot, because in this space here, with this symmetry here, you gain the compactness. This is exactly, the one should know this, maybe also other person, what is called the Italian symmetry. It's exactly this. But in this situation, in this functional, the Italian symmetry is natural. It's not a symmetry that you are imposing, because you just look for, because the natural set where the z, the functions z here varies, is the union of these two sets. Okay?
Because the others are double.
Yes, exactly. Because the link is this one. And so for you, it's good a periodic set, but also an antiperiodic set. And so if you find antiperiodic solution, then finally you have found periodic one. This is the reason. And so this symmetry is in some sense hidden in the problem, and you don't need to impose any further condition on the P. And it is a natural symmetry that comes out from the fact that the fiber of the map P contains 2 points, Z and minus Z. For any P, you have 2 points. For any, X, you have 2 points. Okay? So this is the nice stuff. So now you know that you have compactness conditions that are satisfied, but you can also remark another fact. You can also remark that the P is an even functional. And when you have an even functional that satisfies this compactness condition, if you have done some variational method courses, you remember that there is a method that provides you an infinitely many solutions. This method is the Krasnodębski genus strategy. It is a strategy that provides you infinitely many critical levels characterized as, it's not the minimax, but more or less is a sort of minimax. Okay, on suitable closed subset of the space. Okay, it's not a really straightforward this application, but it is classical. Okay, and so what finally you can prove is that to any pair of critical points of this new action functional that are antisymmetric at 11 sigma n correspond a discrete T periodic generalized solution of the starting problem. Okay, so this we call it hidden symmetry of the functional produce infinitely many solutions. The strategy of the proof in 3 dimensions is essentially the same. You just have to take into account that when you construct your Kusaino-Stiefel map, your map here, the map phi from the quaternions to the purely complex quaternions, that is this map here. This map actually sends S3 to S2 and has fibers that are S1. It's an off vibration. Okay. The fact, so in the Regularized case, you have for any point the counter image as 2 points. Here, for any point, the counter image has an S1 of points. So the set where you try to look for critical points is bigger. Okay, it's simply bigger. You just have to understand who is this set to apply the same strategies. And this set is now I will go back on this assumption, but this set is let me go here for a moment. Is the union on S1 of some functions. Let's see here what these functions. These functions are simply the periodic function, one periodic function when C is 1. Are simply the antiperiodic function when C is minus 1, while when C is another element in S1 is another set. Okay. So actually the same machine of the planar case works here. Let's have a look a little bit better. So we have this phi that induces vibration, okay. In order to make the second step, that means also for the first step, you need a condition on Z. This is a natural geometric condition when you work with this regularization in R3, that indeed is linked to the fact that you started from R4 and you go to R3. So here you did an assumption, okay? And I suggest, if you are interested to understand the real geometric meaning of this assumption, to refer to some papers, in particular this one of Leitzau, 2015. And in this case, you see that the functional is exactly the same as in the Levi-Civita situation. Just here, you have your phi map instead of Z squared. It's the same. It's exactly the same. So your machine works also here. And precisely, you can prove that if you have a critical point of B, and suitable assumption, that is the one that I told you before, then you have also a generalized solution. Okay, this assumption here is the one, the geometric assumption that you can say many things on this, but I just say that it's a first integral of the motion. And this assumption is also straightforwardly satisfied from Dirichlet non-boundary conditions, but it's not these are not the condition I'm dealing with. And also that it's possible to construct, it's not immediate, but it's possible to construct a counterexample for which this condition here is not satisfied. And for this reason, there is not a correspondence between critical points and generalized solutions. You can construct some counterexample. And then the parity of the potential of the functional allows you to apply the same machine of Krasnodębski genus. The same machine on a space that is this one, this space here, the one that I described before. It is a quite, it is a little bit more complicated, but you can prove that it is a infinity manifold of the Hilbert space H1, and that it is modeled on W1 times R. That means that there exists a bijective map with this set. Okay, this W1 are the periodic solutions. And now on this set here, for the function that I wrote, we can construct infinitely many solutions exactly with the same strategy. So we prove that both the functional and the space have some parity, satisfies a symmetry assumption. Then this is a little bit where I start on this point, because the Balanced-Mail assumption, the compact-Mail assumption now is no more satisfied, but luckily it is satisfied a weaker condition. Okay. This also is quite well known. I didn't know it, but I think that this is quite well known in the field of traditional techniques. It's just a weaker condition with the Balanced-Mail condition. And it is enough to apply Krasnodębski-Gilles methods. So these are the levels, the in-sub levels that you can prove that goes up to infinity, and so you have infinitely many solutions, also for the three-dimensional case. So here it's just a complementary result of the Dirichlet problem, but I think that are less interesting because these are situations that can be also covered by some other methods. It's just the existence of a generalized solution for the Dirichlet problem. It was quite a training for when we found the new function as a first result with this one to try to understand how it works, but it's less interesting than the periodic solutions that were not known.